Let us start lecture 39. So, we are left with 2 more lectures, and in these 2 lectures, remaining lectures, we will consider some of the case studies where corrosion happens in case of metallic object, and we will try to understand those corrosion events with the help of mixed potential theory. And in fact, in the last lecture we saw how this mixed potential theory can explain the corrosion event in case of zinc in HCl, and then we tried to draw Evans diagram, which is basically plot between potential and log of current density, and then we tried to consider the activation polarization part only in the beginning, and later on we will also see some examples considering the concentration polarization. In this particular, so that means we will look at some of the case studies or events of corrosion considering mixed potential theory. We will try to understand through this theory. As I have mentioned, that we will be concentrating on the activation polarization part initially and try to draw Evans diagram, but later on also we will look at concentration polarization part also. So, we have 2 situations, one is neta equal to beta log I by I0, another one is neta equal to 0.0591 n log 1 minus I by I max. So, this is basically concentration polarization, this is activation, and in the concentration polarization we would consider cathodic polarization. Now, in this particular junction we would like to mention that we would consider cathodic polarization, not the anodic polarization, because the anodic polarization event is very uncommon. There are 2 possible reasons. One is of course, when you consider anodic polarization, there should be depletion of metal ions in the interface, around that interface due to corrosion event, but since it is anodic polarization, so metal is going into ion form. So, there would be enough supply of metal for the formation of metal ion. So, the depletion of metal ion is unlikely. So, that means depletion is unlikely, and second part is when it is during, of course, during anodic polarization. Since during anodic polarization is actually going to metal ion. And the second part, during anodic polarization there could be a possibility of passivation. This passivation can be explained on the basis of Pobe diagram. So, if you let us say some metal E versus log I, if I consider the Pobe diagram, let us say it looks like this, and this is metal oxide part, this is metal iron part, and this is metal part. Let us say if I am operating at this pH, sorry, this is not log I axis, this is pH axis. So, if I operate at this pH axis, as I go upward, that means if I go on the anodic side or the positive side, neta is positive. So, then initially it is in the metal part, and then finally it goes to metal oxide part. So, then you have actually metal oxide forming on the metal surface, and which can lead to passivation. So, at a large over voltage or positive over voltage, there could be possibility of passivation also, but the main reason is this depletion of metal ion is unlikely in case of anodic polarization. and this concentration polarization happens due to depletion of concentration of ions, but in this case it is unlikely. That is at anodic polarization we would not be able to consider. We will see some of the examples considering cathodic polarization, and of course in the beginning we will consider an activation polarization. In the last lecture at the end we started talking on the effect of galvanic coupling of a metal object which is active with a noble component, and that is what we started looking at. If I see the last part, we started looking at combination of zinc and platinum in acid media. So now you have two beaker, and in one beaker you have a block of zinc, another beaker you have a block of zinc which is connected to block of platinum, and they have the same area which are exposed to the acid medium. This is acid medium, same condition, temperature, pressure, both the cases. In that case we have to draw events diagram, and let us draw the events diagram. Log I, this is E, and we start with zinc, and there, because the anodic reaction is zinc dissolution, and here platinum is noble and zinc is active component. Zinc dissolution is anodic reaction and hydrogen evolution is the cathodic reaction when we have mixed potential theory to be active. Now this is basically I0 for H2 gas evolution. Let us say this is on zinc surface. In this case, this is the case what we are considering now. This is 0, E equal to, and this E is equal to minus 0.76 volt, and this is for zinc plus zinc, and this is for hydrogen H2, and it is lying here for zinc. This is I0 for zinc on zinc surface, I0 for zinc on zinc surface. And then we see a mixed potential. This is my E core, and this particular current is I core of zinc when there is no galvanic coupling between zinc and noble component which is platinum. Now once we have hydrogen evolution on platinum surface, as we know that I0 of hydrogen on zinc is less than equal to I0 of hydrogen evolution on platinum, since this value is close to 10 to the power minus 2 to 10 to the minus 3 ampere per centimeter square, and here it is 10 to the power minus 10 to 10 to the power minus 11 ampere per centimeter square. So this is the difference in their values. When we have this particular, let us say this particular situation now hydrogen evolution would also take place on zinc surface as well as platinum surface, and since platinum is noble, so platinum will act as cathode and zinc will act as anode, but hydrogen evolution can take place on both the surfaces. Now if I consider hydrogen evolution on platinum surface, its exchange current density is pretty high at this point. So this is I0 hydrogen on platinum surface, and E0 of course it would be same 0 because we are considering hydrogen evolution, and then it would also have its own cathodic polarization, and it is cutting here. Now question is, would this be my new mixed potential? No, because as per the mixed potential theory, we see that there will be a possibility of existence of a mixed potential where there should not be no net current flow in the system. Now, in order to have this second criterion to be fulfilled, we must have summation of IC should be equal to summation of IA. So, that means in the system we must have to see that total cathodic current density is equal to total anodic current density. Now, here we have two sets of cathodic reactions, one is on zinc surface, another is on platinum surface, and one set of anodic reactions. So, this is two sets of cathodic and one sets of anodic. Here I am considering two sets, means this is happening on platinum surface, this is happening on zinc surface, but zinc is dissolving from the zinc surface only, platinum would not dissolve because it is a cathodic component. Now, that case, since there are two cathodic reactions, in order to fulfill this criteria, the total cathodic current density should be equal to total anodic current density, I should add up these two polarizations. Now, in order to add up, since it is a log scale, so it will go at this point, because I have to add at every potential I should add this one and this one, these two current densities, and get to the new current density, which is this one. Similarly, here we have to add this point as well as this point to get to the new current density, which is this point, which is new IC, which is IC, let us say this is IC prime equal to IC hydrogen on zinc plus IC hydrogen on platinum, and at this point it is basically IC hydrogen on zinc plus IC hydrogen on platinum. So, like that way we have to add up all the cathodic reactions. Now, if we add up, then if we connect them, then we will see that the added part would follow the red line. And now, if I look at this point, here I have IA, which is this one, and if I try to see the total IC, so these are the 2 points where I could see that at this point, this circle point, I see IC equal to IA, and this IC has two parts, one is this IC, another one is this IC. So, IC on hydrogen evolution on zinc surface plus IC hydrogen evolution on platinum surface. Then I could see that at this point I have two hypotheses of mixed potential theory are met. First one is it is reaching to a mixed potential, and then at that potential I could see that this condition is fulfilled. That means when this condition is fulfilled, so since IC and IA they are flowing opposite directions and of equal magnitude, there will not be no net current density. So, now this particular potential would be nu E core, and corresponding current density, which is IA, is basically I core nu. Now, when there were no platinum connection between zinc, there was no connection between zinc and platinum, only this case I had current density for the corrosion is this one, this particular current density was the corrosion current density. But as we have connected to platinum, which is a noble component, I could see that the current density for the corrosion has gone up enormously, because you remember this is a log scale. And also one more thing, since it is a log scale value, So, when you add this particular polarization with this particular polarization, that the current densities for the cathodic reactions, it will not shift a wider distance, because the scale has to be maintained. That is what there is a small increase on the right side of this point. So, that small increase is coming because of this log scale nature of this x axis. Now, you could see that this case 1, when we have connection of an active component with a noble component, the corrosion rate of the active component goes up enormously. This is the explanation why it goes up with the help of Evans diagram. Now, let us look at a second case. This is case 1. I would say this is case 1. Case 1 is effect of galvanic coupling and with active plus noble. This is the galvanic coupling considering. But remember, when we have seen this galvanic coupling, we have said that they have the same area which is exposed to the acid medium. The area is not changing. The galvanic, that active component has got the some area, let us say 1 centimeter square, then platinum would also have the same area. Now, interestingly, if we have another metal, let us say if it is connected to another component, let us say instead of platinum we add platinized platinum, that case the corrosion rate would further increase. In that time what happens? This particular current density would switch to some other current density, let us say at this point, because current density, exchange current density for hydrogen evolution on platinized platina is higher than that on say plain platinum surface. So, again further if I follow the same way what we have done in case of platinum, this one would be the new mixed potential, and we could see that the corrosion current density has gone up, where this line indicates the addition of this current density, the current density following this particular polarization of hydrogen evolution on zinc surface, and hydrogen evolution on platinized platina following this particular arrowhead. If I see the green arrowhead, this particular polarization. So, that this particular line, this blue line is nothing but the addition of this one and this one. So, then only at this point I could see IC summation equal to IA is equal to I core. So, that way we have discussion or the explanation of increase in corrosion rate when we combine an active component with a noble component. Now, let us consider the second case study, case 2, where we consider the effect of presence of oxidant, or we call it oxidizer, and that should be strong oxidizer. For example, Fe3 plus presence on the corrosion rate of active metal. Now, again let us draw Evans diagram. Now, whenever we have, let us say this is in acid medium. So, if it is in acid medium, we have hydrogen evolution reaction E equal to E0 equal to 0 here, and let us say this is my E0 of this some value, let us say some, this value is in the minus direction. Now, they will have their own mixed potential, this is my mixed potential. Now, Fe plus 3 plus E equal to Fe plus 2, this has got a very large E0. This is almost about close to 0.77 volt, if I remember correctly. Now, if I try to see, this is positive 0.77 equal to E0 Fe plus 3 Fe. So, let us say its position is here. This is I0 Fe plus 3 Fe plus plus on metal surface, because this is in the ionic form in the solution. So, you have a system like this, this is a acid, this is the metal, and on top of it I have hydrogen cathodic reaction as well as this reduction reaction. So, and dissolution reaction is 2 plus, this is my anodic reaction, and these two are cathodic reaction. So, now you could see that this entire corrosion process is divided into one anodic reaction and two cathodic reactions, and both these cathodic reactions are taking place on metal surface. So, that is what we are considering I0 for Fe plus 3 to Fe plus 2 on the metal surface. So, it would have its own activation polarization, cathodic as well as anodic. Now, since this particular point, which is I0 M 2 plus M on metal surface, and hydrogen, this is I0 hydrogen on metal surface. Since these two potentials are lying below this potential, so then everything will be coming between these two extremes. That mixed potential would come in between these two extremes depending on the situation where I have the net cathodic current density is equal to the net anodic current density. So, that particular point we have to find out. So, now without this Fe plus 3 presence, I would have gotten this particular point to be my new mixed potential and corresponding corrosion current density. This is I core, this is E core 1, let us say this is 1. Now, once we have this presence of Fe plus 3, it is a strong oxidant. That means it will have a very large, very high tendency to get reduced, and there would be strong cathodic polarization because it is in very strong cathodic reaction. And remember, all these individual redox reactions or half cell reactions would have their own anodic as well as cathodic polarization. So, this is anodic polarization for hydrogen evolution, this is cathodic polarization for metal, and this is the cathodic as well as anodic polarization for Fe plus 3 to Fe plus 2. So, now it would come like this, and once it reaches to this particular plane, immediately it is seeing that there is another cathodic reactions, which is hydrogen evolution reactions. So, now as per our concept in the previous example, we have to add up the total cathodic current densities. So, now we have to add up that total current densities. So, had it gone through the actual path, it should have been like this, but since there is one more cathodic reaction which is hydrogen evolution, it would add up. Since this is in log scale, so this adding will not go very far. So, it will be small increment as per the value at different potentials. So, then we add up and we get to this, and then if we extend it, we could see that at this point, which is new E core, let us say condition 2, where this is my I core case 2, and then if we extend this particular line, I have two current densities, cathodic current densities, these two. So now let us say this is IH2 on metal surface, or rather I say IH2 IC of H2, and this is IC Fe plus 3 Fe plus 2, and at this point I could see that IA equal to I core equal to IC, and this IC is basically addition of ICH2 plus IC Fe plus 3 Fe plus 2 at E equal to E core 2, the condition 2. So then we could see that again the corrosion rate of the metal is going up, and since it is in log scale, so this corrosion rate increment of that metal is very high. And interestingly, one more thing, if you look at this carefully, had there been no Fe plus 3, the corrosion rate would have been here, and this should have been the rate of hydrogen evolution on metal surface. But once we have Fe plus 3, the corrosion rate is increasing, but the rate of hydrogen evolution on zinc surface is decreasing as compared to the rate what it should have been there without Fe plus 3 presence in the solution. So then you could see that the metal ion on the metal hydrogen bubbling rate, bubble formation is reduced somewhat, and this reduction is coming because of depolarization effect. What is depolarization? Depolarization means what should have been the polarization, now that polarization amount or the over voltage has reduced. Had it been only M and hydrogen reductions, metal dissolution and hydrogen evolution reactions, my over voltage would have been this much. Now with the presence of Fe plus 3, the over voltage for hydrogen evolution is this much. So this is when Fe plus 3 is present, and this is without Fe plus 3. So we could see that the over voltage for hydrogen evolution reaction has gone down or decreased due to the presence of Fe plus 3. That particular effect we call it depolarization effect on hydrogen evolution because of presence of Fe plus 3. So that is what Fe plus 3 is called, depolarizer. And in fact the same effect was seen in this case also. You could see that when the platinum is connected, hydrogen evolution rate on the zinc surface is reducing. So platinum is also acting as a depolarization for hydrogen evolution on zinc surface. So now we have seen two examples. Case 1, when we connect active component with a noble component, and the second case when we have a presence of strong oxidizer. In both the cases I could see that the corrosion rate of active metal is increasing to a great extent. So let us stop here. We will continue our discussion considering few more case studies. Thank you very much.